Let's see whatever the basics are required for this regenerative braking. So for that, I am just taking a motor. Let us assume I am taking a motor. So for this I have given my 3-phase supply. This is my 3-phase supply. So let us assume this is my stator where the winding is made. Let us assume that this is R. Here the Y phase is made and here the B phase is made. Let us assume there is a rotor also. So for simplicity I can take a squirrel cage rotor. So where the rotor bars are kept like this. These are my rotor bars. Getting it? So whenever you give the supply RYB phase sequence, we know the rotating magnetic field will be produced in the sequence R to Y to B. That means in the sequence R to Y to B, where the speed ns is equal to 120 F divided by P. So because of this rotating magnetic field, the EMF will be induced in the rotor. So that depending on how the EMF that is induced in the rotor, that will produce a torque. How the torque is produced, depending on that, the direction of rotation of rotor will be decided. Let us see the case of the speed less than the synchronous speed. So I am again taking, let us assume a stator is there. Let us assume at a particular instant, here there is a north pole, here there is a south pole. Let us assume it is rotating at a speed of ns, which is given by 120 F by P. So now coming to the rotor, let us assume this is my rotor. On the rotor I am just taking 2 conductors. Let us take these 2 conductors. This is my rotor. Let us assume this rotor is rotating at a speed n. So this n is less than ns. So let us take this n is less than ns. So we know the slip is equal to ns minus n divided by ns. This will be because ns is greater than slip is positive. So when the slip is positive, how this is going to affect? Now let us assume, because whenever you want to apply the Fleming's right hand rule, so with respect to the field you have to see, because the speed of the field is ns is greater than n. That means we can tell that with respect to the field, the conductors can be assumed to be rotating in the backward side. So now you can apply your Fleming's right hand rule, where your pointing finger indicates the direction of the magnetic field from top to bottom. Then your thumb indicates the direction of motion from right to left. Then your middle finger indicates the direction of the current. If you apply it, you will get it as a dot. So this will be obtained as dot. This will be obtained as cross. So now this is the direction of the current. So this current, when it is closed from both the sides, like squirrel cage rotor, it is short circuited on both the ends. Like slip ring rotor also has a closed circuit. Now it produces a torque. The torque I can find by using Fleming's left hand rule. If you apply the Fleming's right hand rule, again pointing finger indicating the direction of field top to bottom. Then the middle finger indicates the direction of the current, that current is coming towards us or the finger is pointing towards us. Then your thumb indicates the direction of the torque. So you will observe that your direction of the torque will be like this. This is my direction of the torque. So from this we can tell that if this is my direction of ns, and this is my direction of n, in the same direction the electromagnetic torque is produced. So as the electromagnetic torque is produced in the same direction as the rotation, that's why we can tell in the case of motor the torque is positive. The torque is aiding the rotation in the direction of the rotation. And we have derived the torque equation also in the induction motor. We have written that torque T is equal to 180 by 2 pi ns into SE2 square into R2 divided by R2 square plus SX2 square. This is what we have seen there. So here the slip is positive. If you substitute slip is equal to positive, you will observe this torque will be positive. And if you keep the torque speed characteristics, we have seen there the torque speed characteristics for induction motor. Let us assume I am starting from slip is equal to 1, slip is equal to 0, or we can tell the speed is varied like this. The speed is equal to 0 and speed is equal to ns. So we are going in this direction. So the torque speed characteristics will come like this. It will start from a point, it will reach the peak and then it will decrease. So this is at the speed n is equal to ns. So up to here it is clear to you. So now let us see what will happen if the speed is increased beyond ns, how the torque will come. So this is my torque and this is my value of the slip. So I am taking that here. So let us take the case I am taking my rotor and the stator. So let us assume this is my stator. It is having a north pole here, south pole is induced here. So let us take the rotor again. The rotor has a conductor. Sorry, it is moving little bit because it is coming automatically. So fine, let us assume a conductor is there. Let us assume the rotor is initially rotating at a speed of n. The stator rotates at a speed of ns is equal to 120 F by P. Let us take the case when speed n is greater than ns. So what is going to happen? When speed is n is greater than ns, so with respect to this field, the conductor is rotating in this direction because the relative speed is ns minus n is coming negative, or it is rotating ahead of your stator rotating magnetic field. So now you can apply your Fleming's right hand rule. If you apply your Fleming's right hand rule, like again point finger downwards, then your thumb indicates the direction of the motion. It is from left to right. Then your middle finger will point inwards, or you will get it as cross and you will get it as dot here. Now again you can apply your Fleming's left hand rule to find the direction of the torque. If you apply the Fleming's left hand rule, you will find the electromagnetic torque will come like this. That means we can tell that if this is my direction of the rotation ns and this is my direction of rotation of the rotor, then your direction of the electromagnetic torque will be like this. This is my direction of the electromagnetic torque. You can see here electromagnetic torque is acting in opposite direction to the speed. That's how we can tell the torque is negative. So if you draw the torque speed characteristics, you will get it as negative like this. So you will get the curve like this. So this is when the slip is negative, because slip becomes negative. This is slip is negative. So the curve will come like this. So we can tell under this mode, because the torque is the negative torque, the meaning of the negative torque means it will supply the power back. It will supply the power back to your supply. So it will be regenerating mode. We call it as a regenerating mode. I hope the basic of the regenerating and motoring mode is clear to you. Let us see how can we go for the regenerative braking, how the changes can be applied in induction motor so that we will get the regenerative braking. Because from this we can observe if the speed of the rotor is greater than ns, in that case we can produce the regenerative braking. That means it can generate and send it back, because the torque is in opposite direction to the rotation. Gradually rotation will come down and the torque will become zero when the rotor speed is approaching equal to the synchronous speed. So let us proceed further. So for that I am just making a little change in the curve to represent it more easily. Let us assume this is my positive value of electromagnetic torque. This is my negative electromagnetic torque. So if the slip is varying, that means let us assume this axis is the speed. I am just making some change. That means I have just tilted the angle. So the torque slip characteristics will come like this. It will reach some maximum. It will reach some 0, and from here it will reach this. Okay, let us assume this point I am taking as some point A. Okay, let us assume the number of poles is equal to 4 poles in this case. So generally whenever the motor is started, the motor will start like this. It will go on accelerating, it will reach some steady state point. Let us assume this is my steady state point. That means this steady state point is achieved at a speed corresponding to n. Okay, now if you want to apply the regenerative braking is possible only if the speed is greater than ns. So how to convert this? If I can increase the number of poles, because we know the ns is equal to 120 f by p. So if I can increase the poles, automatically the ns will decrease or the curve will shift. So let us assume I have increased the number of poles to 8. I have made it double. So synchronous speed becomes nearly half. Because poles become double, it becomes half. So your curve will shift. So your curve will shift like this. So this will be your new curve. This will be your new curve. This becomes with 8 poles. This becomes with 8 poles. Getting it? Let us assume already the motor is running at a stable point at point A, running at a speed n. Now suddenly the number of poles are changed from 4 to 8, because this is possible only in the case of squirrel cage induction motor. Because in the case of squirrel cage induction motor, the rotor number of poles will automatically induce when you change the number of stator number of poles. This is not possible in the case of slip ring induction motor. That is a major limitation of this regenerative braking. So let us assume it is a squirrel cage rotor and you have changed the number of poles to 8 poles. Now what happens corresponding to this slip, because it shifts to this new curve. So corresponding to this, because this will be the new point corresponding to this speed, so it will shift to the point B. Let us assume initially this point is A. It will shift from point A to point B. So now you can see the point B comes in the generating mode. So it goes to the generating mode. So regenerative mode means it will generate the power. Torque is negative, so it will supply the power back. So where it is taking that power from? It is taking the power from the acceleration of the rotor only. Because now it is not a motoring action. So whatever motor is having the inertia and rotating, that inertia is converted back to the active electrical power that is fed back to your supply. So the speed will goes on decreasing. So it will go on moving like this. It will go on moving and it will move, and finally it reach this point to again reach the motoring mode. This is my point C. So what care you have to do? If you are not taking care, only changing the number of poles, it will just traverse through this path. This is path number 2. It will traverse through this path and it will reach the point C and again start running as a induction motor at a lower speed. This is not what we want. So what we have to do, whenever the speed reaches near to the synchronous speed, that means at point number B, you have to apply, disconnect the supply and apply the mechanical brakes. So let us see what are the steps to do. The steps are, first step is change the poles of stator. So when you change the poles of the stator, so rotor poles are induced automatically in squirrel cage rotor. So that's why only squirrel cage rotor is used. So whenever it is changed, so what happens? So it starts regenerating and supply the power to source. Okay, then it follows the path capital B small b C and again go to motoring mode. So what we have to do? So when the speed reaches near to B, we have to disconnect the supply and apply mechanical brakes. So this is the procedure to do. So here you have to observe that the amount of regenerative braking or the force, how much fast it will decelerate, will depend on at what instant of this curve you are switching off. Let us assume if you are turning on at this point, like let us assume motor is actually running here. If you are turning off at this point, so it will take little bit more time. But here actually what happens, you can see as the speed is decreasing, the amount of torque, electromagnetic torque is increasing. The electromagnetic torque is increasing means the force to stop it is increasing, so it will decelerate at a faster rate. Whereas if you are switching on at this instant, it will decelerate slowly because the amount of torque as the speed is decreasing, the torque is decreasing. So deceleration will be little bit slow. I hope this is clear to you. So only one thing I want to summarize, that regenerative braking is possible only in the case of squirrel cage induction motor, not in the case of slip ring induction motor. If you want to use it for a slip ring induction motor, it is only possible when you are going the speed above the synchronous speed, like in the case of cranes on hoist, where when you are getting down, in that case if your speed is greater than the synchronous speed, in that case you can apply the regenerative braking for the case of slip ring induction motor. Otherwise regenerative braking cannot be applied.